Okay, hey everybody. This is lecture 9, Wednesday's lecture. You can see in quotes it says it's April 29th. I'm recording it on Sunday, April 26th. Thank you everyone for watching it. This lecture is entirely on images. Images are, of course, not a Unix or C++ topic, but we're going to learn a little bit about images because it's going to allow us to do our big project, Project 3, where we really exercise our C and C++ skills. So here's some background on images. This is my daughter, Charlotte. Charlotte is livening up the presentation, and she actually wrote all of her signs backwards because there's a mirror image effect with the camera. So background on images. Images are two-dimensional arrays of pixels. What is a pixel? I'm going to read this exactly. A pixel is a minute area of illumination on the display screen, one of many from which an image is composed. So let me show you an image real quick. So here's actually the image that you're going to use for Project 3A. And if I zoom in on it a lot, you can see this one little square here is a pixel. It kind of loses its boundary because there's other pixels nearby, but every image is just made up of many, many pixels. They're really a two-dimensional array of pixels. So each one is a row, and then there are many rows in height. Every pixel is made up of three colors, red, green, and blue. This is not the color scheme I learned when I was in preschool. In preschool, I learned that the three primary colors were red, yellow, and blue. And if I wanted to make green, then I made green out of blue and yellow. And when I used Play-Doh, that's what happened. Computers use red, green, and blue, and you'll see them abbreviated R, G, and B. So every pixel, and you can think about images typically having on the order of 1,000,000 pixels. Every one of the 1,000,000 pixels has some amount red, some amount green, and some amount blue. And you can just think about the amount in each scored from 0 to 1. So here I have some examples below. If it's 100% red, 100% green, and 0% blue, then that pixel would be colored yellow. Again, that's backwards from what I learned when I was in elementary school. If it's 100% red, 0% green, and 100% blue, it would be purple. That fits preschool Hank's thinking. If it's 0 red, 100 green, 100 blue, that's cyan. And then if you have 100% in each of the three, then that's white. Okay, so the colors in the previous slide, we were thinking about representing them between 0 and 1. But I actually didn't specify what the resolution was. So the resolution could be a double, and or it could be even many doubles. We could say we need to know the color resolution to millionths of a percent or billionths of a percent. And so the question I would ask is, how many bits should you use to represent the color? And so then the question I asked to motivate that, okay, good, noted, is can your eye tell the difference between 8 bits and 32 bits? And the answer for the most part is no. The human eye can only distinguish about 10 million colors, assuming you're not colorblind, then it's less. And if we use only 8 bits per color, then we'd have 8 bits per color and 3 color channels, red, green, and blue, RGB, and that would give us a total of 24 bits, and 2 to the 24th is about 16 million. So if we use only 8 bits, we get 16 million colors. Our eyes can distinguish about 10 million colors. So 8 bits is probably sufficient. Now, as it turns out, the 10 million colors we can see are not a subset of the 16 million colors a computer can represent. They have differences, and there are colors that we can see that a computer cannot represent. And certainly colors a computer can represent that we can't see. We know it can represent 6 million more colors than we can see at the most. But I think it's interesting they're just colors that we can see that a computer can't represent. And so since we know we can represent them with 8 bits, that's a single byte, an unsigned car. And so then where the previous slide we had 100% and 0%, now we can represent them as unsigned cars. And here we can say red, the color red, is represented as 25500. The color green would be 02550, and the color blue would be 00255. So there's a question of how we should organize a struct. That's not true. Uh, there's a question of how we should organize a struct for an image. So an image is actually a three-dimensional array. It has a width, and it has a height, and then it has three color channels. And so there's actually two decision points. One decision point is on how you want to represent a color, and one idea is that you could have an RGB struct, and then you can have a two-dimensional array of RGB structs. Another idea is that you could have just three unsigned cars, and then you could have a three-dimensional array corresponding to those three unsigned cars. With the pixels, one idea is that you can have an array of row pointers, and within each row pointer you can have pixels along that row. And the other is, again, that you can just index into some big two-dimensional array. So let me do a little coding real quick to show what I mean. I do use that. You're totes adorbs. She got upset as she walked off because she's cray-cray. So one idea is that we could do like this and have a pixel like that. If we wanted to, then if we wanted to make an image, then we could have, for example, a pointer to arrays, or a pointer to an array of pixels. That's what I want to say. And then if we're allocating it, then we'd say something like pixel equals malloc of width times height times size of pixel. And then we could say, like, if we knew that we wanted to access a specific pixel, like the pixel WH, then we'd say pixel of, and now there's an indexing that has to happen here. 0, 0 is the 0th pixel. If this is the first coordinate is the row, then that's pixel 1. That's pixel 2. And then 0, 1 is the pixel W. And so on. So the row, as you go along the width, that's actually it's a column. Whoops, that's the column as you go along the width. I've totally screwed this up. The first value is going to be the X location, and so the first column will be the first parameter will be the column. Like so A, B, C, D, I, J, K, L would be the first row, E, F, G, H would be the second row, and A, B, C, D would be the third row. And then that's the first column. This is the second column. This is the third column. And this is the fourth column. So when I say 0, 0, well, obviously that refers to I. But when I say 1, 0, that refers to J, which means that the first coordinate is the column and the second coordinate is the row. Okay? So if I had .38, I think I'm doing okay. So if I have this where I want to access some given row and column, just for the record, some given row and column, then the formula for if you have a two-dimensional array, let's put some specific numbers out here. If we have 1024 in width and 768 in height, then that would be how many pixels we have. And if we're talking about sum, row, and column, then really I should represent it like this. Then we would take the row times 1024 plus the column. That would be the indexing method. Okay? And so if we go down here, then if we wanted to access the pixel, we'd say row times 1024 plus C. And if this was of type pixel, like we have up here, then we could say that dot R equals, and this dot G equals 255, 0, 0. Now how can I put 1024, 1024, 1024? The other way to play this game is to not have one of these pixels, and instead when we have an image, we have an unsigned car, and if we want to access R and C, then now it's a three-dimensional array, and we would say 3 times R times G times R times 1024 plus C plus 0. Like that. And so this would be the way we'd access it as a three-dimensional array. So what I saw last year was that most people left it as a three-dimensional array. Wowza. That's a direct hit. My 10-year-old son just got me across the nose with his Nerf gun. So what we saw last year was that people were getting three-dimensional arrays, and they were doing indexing like this indexing here. That said, this indexing, you really only want to think about it and implement it once. What I saw is that people had this indexing over and over and over again in their code, and they would make subtle mistakes here and there that they'd spend a long time tracking down. So I think the three-dimensional array direction is a fine way to go, as is the one where you have a pixel struct. I think they're both good. But if you do the three-dimensional array, I would encourage you to isolate the logic for the indexing to one location and then in a function, and then use that function over and over and over again, rather than re-implementing this logic where you're going to get it wrong sometimes. Okay, so that's it for the coding I wanted to do for these decision points, whether you have an RGB struct or 3 unsigned integers. I guess I didn't get into this one pointer per row versus just indexing it. I did this where we just index it as a two-dimensional array. You can break it down and actually have 3 distinct levels of arrays if you want to, and if that makes sense to you, that's what you should do. There's really no downside to it for this project, and you're in charge. The next topic I want to talk about are image file formats. And so I put up 4 image file formats that you're probably familiar with: PNG, GIF, TIFF, JPEG, and one that you are not. The reason I put up the one that you are not, PNM, is because that's the one we're going to use this quarter, and it's unusual, but there's a reason that we're using it. So what are the trade-offs? Most image formats are hard to read and write, and so people, I love you, sweetie. So people use libraries to encapsulate their reading and writing. They have complex binary formats, and it's just hard for me to hand you a PNG file and then for you to write a reader for it. That's like a quarter-long project, I think. And so you need to you don't want to do that. I don't want you to do that, and so you use a library. But the libraries are problematic for this class. They're problematic because sometimes they're hard to install. Sometimes they just don't work out. And then sometimes they have differences over the different platforms, and we all think that we're writing the same files and reading the same files, and then it turns out that we're not, and those differences creep up later. So here are the problems I've identified, and so of course what you're going to see on the next slide is that PNM solves those problems, and that's mostly true. So what is PNM? PNM is part of the PBM library. The key advantage of the PBM library is, again, it's an obscure file format. It's very easy to write and read. But the disadvantage is it's not supported by many tools. So that is a disadvantage, right? If I hand you PNG files, our web browsers can look at them. If you're on a Mac, you can just say open on the terminal and it will find the right file format and open it up. PNM, it doesn't work so good. So it's not supported by the infrastructure that we're used to. However, there's a package that can convert to from PNM to PNG or JPEG or whatever, and it's easy to work with. And I'll show you how that package works. Actually, I'll just do it right now. So here is 3a input.png. So this is the file we just looked at. And then here is 3a input.pnm. And so this is a binary file, and it has a little bit of ASCII header information. And then when you see these @ signs, this is all binary data that VI is not showing me. And so it's a simple format. But if I want to convert it to PNG, then I have installed a command line tool to do this, and I would just say pnm to png, 3a input, this is our redirection, pnm, 3a input.pnm, and output to hank.png, and I can open hank.png, and there it is. And so I'm going to say this in 2 slides, but I guess I'll say it right now. What I observed last year is that people who were using Macs did not install this library. This does not come natively on Mac. I made a point of installing it. And it's really great because as my program is writing PNM files, I can immediately see what it's writing, and that makes my debugging cycle a lot shorter, and be able to debug, ask questions from a debugging perspective and get the answer right away is really good. So I encourage those of you on Mac to pursue installing these PNM tools. It'll be a new experience for you, but it's a good experience to install software if you haven't done it before. Okay, so here's the package that converts from PNM to PNG. It's a set of command line tools. Here's the documentation for it, and if you do some Googling about Homebrew or Mac ports, then you can figure out how to get this stuff installed pretty quickly if you're on a Mac. Good news is, and this again is in 2 slides, if you're on a Linux box, it's there for you automatically and it just works, so you don't have to do that step. Okay, here is the PNM format. We already looked at it in VI. There's actually many PNM formats. We are always going to use the P6 variant. So you don't need to worry about adding support for the other formats. Here's actually a new Unix command, head. Head just shows you the first few lines of a file. In this case, it asks for the first 4 lines. The first line is P6. That says it's the P6 version of the PNM file format. It says the number of pixels in width, the number of pixels in height, and then it always has, for our cases, it's always going to have 255, and then the binary starts. Now, of course, this is a P6 and a new line, a 1786, a space, a 1344, a new line, a 255, and a new line. And as you're reading out these first little bit, make sure that you read out those new lines. We had problems last year where people would read all the way to the 255, but not the new line, and they read the new line as the first character of the data. And what happened is they read the new line as the first red, and then the first red was read as the first green. The first blue the first green was read as the first blue, and the first blue was read as the second red, and so on. And they got images that looked and structure exactly like they were supposed to look, but it had been through some psychedelic process, and the colors were all wrong. So make sure that you're reading these new lines out, and that you get the position, the file position offset, so that you're exactly at this location when you read all of the data in. Here's a new string command. You remember I talked about the string commands earlier in class. This is scanf. So scanf is just like printf, except for printf prints and scan parses. And the S part, because you see there's 2 S's here, this first S means it's parsing from a string. So this is a good command here. It says scanf string %s new line %d space %d new line %d new line. This would scan out exactly what we're expecting, and on this string right here, it would give the magic num string would be assigned p6, the integer width would be assigned 1,000, the integer height would be assigned 1,000, and the integer max val would be assigned 255. So I think you're going to need something like this in your Project 3A code to read the header. Project 3A, you will be reading images and writing images and doing one very simple manipulation of an image. Okay, so here's some of the stuff I was saying before. Last year, when we did this, the folks with Linux were very happy because this PNM format that's so simple to write to and read from was supported by default. Folks with Macs took one of two strategies. Some found a website where they could upload their file and inspect them. They could upload their PNM files, and the website would convert it to something they could see on their browser. It was a time-consuming process where they would have to click through advertisements and so on. I would really encourage you guys to follow the second path, which is you install programs to convert from PNM to something the Mac can support. I just think that you're going to find that 1 hour of pain where you learn how to install software will be beneficial to you in the future when we have to continue installing software for your later classes, and also it just makes debugging so much easier. So last thing here, Project 3A, I'm going to post the prompt later tonight. I'm giving you quite a bit of time to do it, and I don't think it certainly will not take 10 days. This is a project that you could whip out pretty quickly, but I just want to make sure that everyone has time to get this completed. As I've mentioned several times, we're going to have probably 9 pieces to this project, maybe 8, maybe 10, maybe 12, but they all build on each other, and I'm not going to give away the source code, so you've got to do it. So if you don't do 3A, you can't do 3B, you can't do 3C, and so on. It becomes a cascading set of problems. So I want to give everyone time to get it right. I also want to make sure that I'm around to be there for office hours and to help answer questions. So what are the tasks? You're going to make a struct to contain images. You're going to read images from the file. The simplified format that I'm referring to here is PNM. You're going to write image to a file. You're going to have a function that modifies the image. It's going to take the image and it's going to make a yellow line across the diagonal. And then you're going to have a program that puts it all together, that reads, that modifies, and then writes. So that's it. I will be in Rhode Island. I'll arrive very late Monday night. And I'll be there Tuesday, Wednesday, and Thursday morning, and I'll be flying home Thursday afternoon. I will be checking email, and I'll try to respond to issues as they come up. Our GTS will continue to hold office hours, so Matt's office hour on Monday and Tuesday, and Nasansa's on Thursday will all be held. And of course there is lecture on Friday, and I will have an office hour on Friday. So the only canceled office hour this week is Wednesdays. If anything's confusing, please let me know, and we'll try to get it cleaned up. And again, thank you for taking the time to watch this YouTube lecture. Okay, bye guys.